Hi everyone. In this video we're going to continue on with section 6.3, which involves exponential functions. And so in the last video we talked about how to do arithmetic or certain arithmetic things that we could do with exponential expressions, and so now we're stepping it up into an exponential function. Okay? So an exponential function is a function of the form c times a raised to the x power. Okay, and so a is a positive number. So the base of our we have always a base and then an exponent. Okay, and then a number out in front, and so it could be 1. In that case, the number usually goes away, but if it's not 1, then the number will actually be there. Okay. And so I'll always refer to them as base and exponent. And so whenever I do that, keep that in mind, and that'll hopefully keep it straight for you. Okay. So we have c times a raised to the x power. A is some real number where it's not 1, because if it's 1, then everything's always 1, and it's no fun. Okay. C is a real number, not non-zero, because if c was 0, then everything would be 0, and that's no fun as well. Okay, and then a is often called the growth factor, and c is called an initial value. So an exponential function is often used to evaluate things in real life. Okay, and so we might be evaluating or trying to describe some situation using an exponential function, and oftentimes it is the growth rate of something. So maybe how cells how cells react to some stimulant, how they grow, or how many grow or die, and we can often use something like an exponential function to see that. Okay, so that's an introduction to exponential functions, and it's true, this following fact is true, but it's not going to really come into play for us. For an exponential function, c times a raised to the x power, the following is true. Okay, so the function evaluated at x plus 1 divided by the function evaluated at x is equal to a, and this is trying to get at this growth factor thing. If I increase x by 1, then I'm growing some a amount, and that's what it's saying here. You don't really need to worry about that. So here's this sort of fact sheet about certain exponential functions, and we're going to use this to help us graph and evaluate exponential functions. Okay, most often we're going to use them to graph, but we will also use some of these to help us evaluate or solve for certain functions. Okay, or solve for certain things. So the first property here is that the domain of an exponential function, and actually I guess before we start with that, we should look at this little qualifier here up top. An exponential function where the base of the exponent, or the growth factor, if you want to think of it that way, is greater than 1. Okay, and so something like 2 raised to the x power fits into this thing, but if I had something like 1/2 raised to the x power, which is possible, that still is an exponential function, that wouldn't fit this statement up here, and so we don't want to use that. Okay, or it doesn't apply. These facts don't apply to something like that. But the first step, or first property here, is that the domain of this exponential function, where a is greater than 1, is all real numbers. Okay, and so all real numbers you could write like this, or negative infinity to infinity using interval notation. Okay, and the range of this exponential function is 0 to infinity, okay, or positive real numbers. So if you think about the function 2 to the x, there's no number x where I substitute x in and a negative number comes out. Okay? No matter what I do, it's always going to be a positive number. So domain is all real numbers, range is positive real numbers, or domain is negative infinity to infinity, and the range is 0 to infinity. Okay. As such, if we move on to the intercepts, which we are of course interested a lot in before, and we still are now, there aren't any x-intercepts because the range is from 0 to infinity, non-inclusive. It never gets to 0, hence no x-intercepts. Okay? And then the y-intercept, interestingly, is going to always be 1. Okay? All right, so a y-intercept is always 1, no x-intercepts. The x-axis is a horizontal asymptote as x approaches negative infinity. Okay? That's not going to be super important for us, the whole fact, but I will often ask where the horizontal asymptote of the exponential function is. And so you'll want to keep that in mind. By default, if I have something of the form a to the x, just a number raised to the x power, the horizontal asymptote is 0. Okay? Hence, it connects because there aren't any x-intercepts. Okay? A horizontal asymptote means that it will get arbitrarily close to that number, but it'll never actually hit that number. That number that it gets close to but never hits, if you look at the range, is 0. Okay? And couple that with the fact that there are no x-intercepts, everything makes sense, hopefully. All right. So that's number 3. Number 4 is that function is an increasing function, and it is 1-to-1. Okay, so we talked about these types of properties last time, but it's an increasing function, and it's 1-to-1. All right. The graph of the function f contains 3 points. It contains actually more than 3 points. It contains an infinite number, but it is assuredly going to contain the points satisfied here. -1, 1 over a, okay, 0, 1, and 1a. Okay, and then number 6 is not really going to be important to us, but it would be in something like a calculus class. The graph of f is smooth and continuous with no corners or gaps. Okay, and so that's a lot of information, but what does an exponential function that fits this form actually look like? Well, it looks like this. Okay. So you have your x and y axes, okay, and as the properties say, the 3 points that you really need to use to graph these are 0, 1, 1 over a, and then -1, 1 over a. And so you'll see, as it said, it's always increasing, so it's always going up. It comes down and gets very close as you go on to negative infinity out this way. It looks to get very, very close to the x-axis, which is the line y equals 0, but it never hits it. And so that's the horizontal asymptote. Okay? The y-intercept is 1 here, and then there is no x-intercept because we never hit the x-axis. Okay? So that is the basis of an exponential function where a is greater than 1. Okay. So as a quick next type, what if the function is between 0 and 1? Okay, so that would be the number like 1/2 raised to the x power. Okay, whatever number is inside of here has to be between 0 and 1. Okay, so what are the properties of that? Well, just like the last one, the domain is the set of all real numbers, okay, and the range is positive real numbers. So it shares that with the last one. There are no x-intercepts, and the y-intercept is 1. It shares that, okay, and this is where it starts to get different. There is a horizontal asymptote as x approaches, and the x-axis, or the line y equals 0, is the horizontal asymptote, so it shares that with the last one, but this time the asymptote happens as x approaches positive infinity, not negative infinity. Okay. Step 4 is sort of the big difference with the first one. Now, instead of an increasing function, it's now a decreasing function, but it is 1-to-1, okay, which means it passes the horizontal line test. And the graph of the function contains 3 points, just like the last one. -1, 1 over a, 0, 1, and 1a. Okay? Now, those are similar, but actually they're the same function, or they're the same points, but when the number is between 0 and 1, it acts differently than when it's greater than 1. Okay, the graph is, in step 6, graph is smooth and continuous, no corners or gaps. Again, that's not important to us. But here is the graph of an exponential function where a is between 0 and 1. Okay, and so you'll see it's very similar to the last one, but it's now decreasing. So basically what we did was we reflected it, or flipped it, over the y-axis. Okay, so before, when a was greater than 1, the line looked like that. Okay, what we did was flip it over the y-axis. Okay, and that's what happens when a is between 0 and 1 instead of greater than 1. Okay, and so that's where we're going to end this video. When we start the next video, what we're going to look at is actually graphing exponential functions. So we're going to take this basic form, either this one when a is between 0 and 1, or this one when a is when a is greater than 1. We're going to use these base functions and then apply transformations to them to get our ending function. Okay, that's the end of this video. There aren't any your turns, but there will be your turns, of course, in the next videos.